Hey guys, this is Ryan. So I wanted to approach and talk about the question from the quiz on Friday where we had Jalen Hurts throwing the pass to Devonta Smith in the end zone. So this was the modified version of the one from the assignment. If you can't see it, we basically had the runner could run 40 meters in 4.54 seconds. This was the runner. At the end of the day, for the throw, the runner is going to have to go a total of 45 meters, and then the pass is going to have to go 50 meters. I think that was everything that was necessary, and everything else was superfluous. And the idea here is that basically the runner is going to start from whatever position they start at. They're going to run this distance of 45, and in the same time, the pass is going to go off. So the idea here, and the idea for this question, was to get this pass to go, to get the time and then use that. And a lot of people did it in the same way that the other video was done. Now, the other video was made for this set of questions where you were guided through the question with how long does the ball have to be in the air, how high does the ball get, what's the initial velocity, then what's the angle of launch. And I was really just asking what's the initial velocity and the angle of launch, which, remember, velocity is both a direction and a magnitude and a direction. So if I ask what's the initial velocity, technically I'm also asking what's the angle of launch, because you can't have a velocity without a direction. But that being said, they split it out, but regardless, I just wanted to approach this question in a different way that is a bit more straightforward, and then I want to address where everyone got lost in the other video. Okay? So with these sorts of questions, I really think that your best bet to figuring out what equation you're going to want to use, which you're typically going to be using one of these. You're either going to be using S equals V naught T plus 1/2 AT squared, or you're going to be using the V squared equals V naught squared plus 2AS. And there was another equation that was in the video that is specific to certain situations, and we have to be careful about just using it carte blanche. And there's a reason I didn't give it to you guys for this problem. So what we want to do is remember that anytime I'm using anything in this class, I want to make sure that I'm considering the components. So here in this problem, if we think about what happens to what is the x position over time, right? The x position over time is just going to be, a graph like this. If I were to do, x position versus time, it's just going to be a graph like this where the x position is constantly changing in one direction, right? It's you can also think of it, if we wanted to just draw it without the graph, I could just draw it and I could say, well, the x position starts here, and then if I just trace the x position over time, it's going to go and it's going to end up over here. All right? And it's going to do that at a constant speed because there's no forces in the x direction, right? And if I want to think about what's happening to the y, it's going up, and then it's coming straight back down that same path. And it doesn't go below. I just wanted to make sure you could see that I have the arrow, right? You can think of it this way. Up. It's going up. And then when it gets to the top in the middle here, it's going to come straight back down. All right? Now, when I say straight back down, I mean if we consider just components. So it's important to consider the components, and I just realized that I put a bunch of stuff off screen. Sorry about that. Let me grab that. That should now be on screen for us. Let me just fix this. All right, there we go. So when I said the equations, I wrote them up, and I put the info there. So either way, let's take a look now and consider some of these things to figure out what equation we want to look at. And remember, we have to break these into our components. So I wrote x0, y0 because s is technically displacement. It's the difference between final and initial position, remember? So I want to look at x0 or y0. Well, my initial position is obviously right here. Well, I guess maybe not obviously, but our initial position is right here. I get to define where my, displacement is in the x direction, and I can just start this at 0, and then basically if I'm here, this might be, whatever number of meters this is. And remember, we didn't do any conversions for this problem. I set everything to meters. So my x initial position, I'm just going to say that's 0 meters. That makes sense. And my y initial position, I mean, that can also be 0 meters. I mean, technically it's starting at the, arm height of the passer. But as I said in the problem, we're just going to consider that the release and catch height are the same. So, I'm just going to start this and make this black line be 0 meters as well, right? That's 0 meters in the y direction. Okay, so now S is displacement. We want to consider what's our displacement. Our displacement in the x direction for the ball is 50 meters. The ball has to go 50 meters to get to where it wants to go. It has to go from the first red dot to the second red dot. Those are 50 meters apart, all right? And that's part of the question. It was said that the ball has to travel 50 meters in the air. And our y displacement, we have to remember, it's y final minus y initial. If it starts and ends at the same height, the y displacement is 0 meters. All right, but we know it, right? It's 0 meters. Now, this is if we consider the whole pass. I know there was the way that you break it into half, and we'll cover that. But for the whole pass, the displacement is 0 meters in the y direction. And you're like, oh, well, it's all the way over there. That's all in the x direction, right? This black line is along the x direction as I've drawn it up here. You can see that. So v naught, remember that's initial velocity. A lot of people get into this habit of just plugging in 0 for v naught in places like these equations because we do that a lot. When do we do that, though? We do that when we have some platform and some guy is like dropping something off the platform. When we have, a helicopter. Ooh, that's a beautiful helicopter. Here, I'll give it a tail. There we go. Beautiful helicopter. And you have something being dropped out of the helicopter. Why is it 0? Because the initial velocity in the y direction is just 0 because it's being dropped. We can't just plug that in everywhere, okay? That is specific to the problem. That's why we write these out. That's why I really, really suggest you think about these. If my initial velocity in the y direction is 0, which way is it being passed? Well, let's, draw out a little triangle here, and these are my initial velocities, right? I connect head to butt of these arrows, and then at the end of the day, I connect the start to the end. This would be my initial velocity. This would be my initial in the x direction, and this is my initial in the y direction. This is how we do components, right? If I make the y, this y piece of the triangle 0, what do I have? If I make this be 0 height, well, I just have a horizontal line. So when we were dealing with the gun problem and we were firing horizontally, we had 0 initial velocity in the y direction. That's why we had it in that case. We need to consider these things. The ball is being thrown at this angle, right? You can see it in the drawing here. I mean, even if you don't have the drawing, I think we can all understand that if I throw a ball straight forward, as straight as physically possible, I'm not going to be able to send it a very far distance, which, even if you don't watch football, 50 meters times 3, because remember, there's approximately 3 meters in a foot, right? That's 150 feet. That's very far, all right? So we know that there has to be some kind of up to it. Our bodies naturally know this. If I want to throw something a long distance, I'm probably going to be throwing it like 45 degrees is usually like a good guess, but like, I'm going to be throwing it at some angle up, So either way, all that comes down to the fact that we don't know our initial velocity in the x or the y, but this is what we're solving for. We want to know these. When I say what's the initial velocity, obviously this is what we're solving for. So we need to figure these out. What's our final velocity? Now, this is another really big bugaboo that I have that I see a lot of people doing. They're like, oh, the ball, it hit the ground, the receiver caught it, so the final velocity is 0 because he's holding it. He caught it. Remember, we stop immediately like instantly before, the instant before that happens. Because we're not dealing with momentum. We're not interested in the energy of the system. When we get to those things, we'll see that we actually care once it's caught, once it hits the wall, once it hits the ground, like whatever the problem setup is, we'll care about it. But for now, when we're dealing with kinematics, kinematic means in motion, right? It's the science of things in motion. So once it's stopped, I don't care about it anymore. So we want to stop our consideration before it stops. So our final velocity in the x direction, well, you know, I could skip ahead and I could say, well, we know we're not going to have an acceleration in the x direction. And we know that because acceleration, right, force is equal to mass times acceleration. That's the only way to get an acceleration is with a force. And we don't have any air resistance, so there's no forces in the x direction. If I were to draw, you know, here's my ball and I was going to draw the free body diagram, I really just have Fg. I don't have a normal force. I don't have anything else, right? It's not touching anything. It's in midair, right? I would have like air resistance opposite the direction of motion, you know, probably at some angle more likely if it's going up. But regardless, we don't have air resistance. This problem's not an air resistance problem. So we don't have any forces in the x direction, so we don't have any acceleration. So the final velocity is actually just going to be the same as the initial velocity. It's just going to be the same as v naught. But I don't really need it either. I don't have v naught either. So, you know, we're not going to end up needing that, but I just wanted to point that out. And then in the y direction, the final velocity is not 0, right? The velocity up here in the y direction is 0, okay, at the apex. But at the end of the throw, because here we're considering the whole throw, right? This is the whole throw. We don't actually know what the final velocity in the y direction is. I mean, I can give you a trick and say it's going to be the negative v naught. That's only going to be true because it was released and landed at the same height, right? Everything, it both released and landed at this height. So we know that's a thing, but that's just a trick. So I'm not going to include that. I'm not going to include this. We're just going to write like a slash because we don't actually need these. We don't have them, right? We want to consider things we have. Acceleration in the x direction, I already told you we have no forces. We do have a force in the y direction, which means we'll have an acceleration and it's gravity. And that's nice and easy. We've got g. And we're going to say negative 9.8 meters per second squared. And we want to include the negative here because I said up is positive y. All right. And now time. Time we don't have, right? Time we don't have. It's going to be the same for both, right? There's not time I could take out of this like thing and I could say, well, time is the same for both, obviously. If the ball starts here and ends here, the components don't matter. The time for it to go up and back down in the y direction and the time for it to go from start to finish in the x direction have to be the same because the ball didn't land in two places that are separate at the same time. Like it you know, time is time, and it's independent of the directions. So the trick to this question is that we can find time. We find time using the runner's information. We know the runner starts wherever. He starts like here or whatever, and he has to run this distance, and we have all the information we need to get that because I said there's no acceleration for the runner. So for the runner, we can use this information and we can get the time. We can say, and most people got this. Most people did this pretty well. So we've got the runner. Let's use these equations exclusively, these ones on the right. I could use the shortcut because I know there's no acceleration for the runner because I said that. But let's just consider that. And remember, I'm not using these numbers in this. This is for the throw, okay? Or for the ball, I guess I could say. But regardless, the runner, he goes 40 meters in 4.54 seconds. Okay, let's throw in S equals V naught T plus 1/2 AT squared. If there's no acceleration, because he's like running horizontally, right? And we're not worrying about his acceleration. He's running at that's his constant speed, okay? Yeah. Then we know S being 40 meters. is equal to v naught, which is what I'm trying to solve for. It's basically the running speed of the runner, times t, times the time, which is 4.54 seconds. And that's going to give us 8.81 meters per second. Now, I know a lot of people used v equals delta s over delta t. Literally, it's the same thing. This is only valid when a is 0, when there's no acceleration, which is why I wrote the whole thing out here and I crossed off a. You get the same equation. You can see it if I just rearrange things. I move the t over to this side, and I have s over t equals v, right? Same thing. But I just wanted to clarify that's only when acceleration is 0, which in this case it is, so that's fine. Either way to get it is fine. Once we have that speed, we can use this equation again to solve for this, to solve for the t, right? So the s of the runner is going to be v runner times the time that it takes him to run that, plus the 1/2 at squared. But again, the runner doesn't have any acceleration to them. It's just, we're not worrying about it. We're just assuming that there's some special thing where they started running beforehand maybe, and that's the point that it starts. Don't worry. The point was just we didn't want to overcomplicate this problem. So s of the runner, the distance the runner has to go was 45 meters. For the actual throw, it was 45 meters. I used 40 because this is how we were getting their speed. It was the given for the speed. And then 45 is how far they had to go to actually make this catch. So 45 meters is equal to, and we plug in the speed of the runner, 8.81 meters per second, times the time that it takes them to do that. And you can then see if I move this over, 45 divided by 8.81, I get, I think it was 5.1. Yeah, 5.1 seconds. All right. So what we've just done is a bunch of stuff that let us say that the runner is going to make their run in 5.1 seconds. And most people got this, like I said. So we know the runner will be able to run that distance in 5.1 seconds. If the throw is going to reach them, the throw has to also take 5.1 seconds if both things happen at the same time. Okay? So if this happens at the same time that this happens, they both have to take 4.1 seconds. Or 5.1 seconds. Okay. Now, here's where the big diversion happened. A lot of people were using the video method, and they were doing something about the halfway point. I got a trick for you. If we look at what we have and what we don't have, let's just take a look. We have, we want an initial velocity, right? This is what we want. We now have a time, which plugs in here and here. In the x direction, acceleration is 0. In the y direction, acceleration is gravity. So we have that for both of them. Time is the same for both. And the displacement we have, right? I said we have displacement is right here. So we can actually just take this equation and plug everything in and solve. And if we do this, remember, we need to break it into components. So we'll do it for the x first. We've got Sx equals v naught xt. We don't need an x on that because time's the same for both. Plus 1/2 ax t squared. There's no acceleration in the x direction. We showed that over here, right? No acceleration in the x direction. V naught is what we're solving for. T is 5.1. And the Sx is the distance he has to throw the ball, which is 50 meters. That was the passing distance, okay? So that's going to be V0x. And, you know, what we get here is that V naught x is equal to 9.8 meters per second. That has nothing to do, this has nothing to do with gravity. It's not related to gravity. This is a velocity, meters per second. The numbers just happen to work out. I should have checked them beforehand. The numbers just happen to work out to be 9.8. Don't let that confuse you, okay? Unfortunately, I couldn't even like round it. It wasn't like, it's like 9.80 something. And I'm like, okay, great. I messed that up for you guys. Sorry. But regardless, we need to understand that velocity and acceleration are two different things. So We have v naught in the x direction. This is how fast the ball was going in the horizontal component when he threw it. And then we can do the y, and we can actually do the exact same thing. Sy equals v naught y t plus 1/2 a y t squared. And here again, we're going to plug in 5.1. Acceleration, we have to plug in negative 9.8, right? V naught y, we can't plug in 0, right? We're not crossing this off because there is an initial velocity. This is what we want. And then s of y is going to be 0 because it starts at the ground level, it goes up, and then it comes back down to the ground level. Okay? So, or, you know, hand height for the receiver and thrower, but either way, same height. So, the change in height, which is s, is 0. S sub y is 0. And we plug this in 5.1, and what we get, I'll plug all these in, and we'll make a nice little equation here. We've got 0 is equal to v naught y. I actually don't want to parentheses there. V naught y times 5.1 seconds plus 1/2 negative 9.8 times 5.1 squared. When I move this to the other side, the negative goes away, right? Because we subtract it, and this 9.8 had a negative in it. So we get 1/2 times 9.8 times 5.1 squared, and then we're going to divide by 5.1. So we'll actually just get 1/2 times 9.8 times 5.1, because when we divide, we lose one of the 5.1s. And the number we're going to get is, we're going to get v naught y is equal to 26.84 meters per second. I'm sorry. That is the final number we end up with. We get 24.99 meters per second. Okay? This is in the y direction. And now, all that's left, once we have all of that, we need to remember that a velocity is not two components, right? It's those two components put together, right? I can't just say, this is not my answer. Giving me both of these is not the final answer. The answer we have to do is we have to take the x component, and we take the y component, and I'll make it a little taller because we know the y is a good bit bigger, so this isn't to scale, but that's fine. And what we do is we got to connect these to make a vector. Okay, this is vector math. This is a square root, or this, I'm sorry, this is a right angle, and we've got some angle here above the horizon. We'll call that theta, right? You're usually going to measure your angles from above the horizon. And here, this will be our v naught. This will be our v naught x, and this will be our v naught y. When I say v naught, I mean v0. It's just another way to say the same thing. And now we have a triangle that has these numbers here. And it's important, really important, to know how to do this math. The hypotenuse squared is equal to the sides squared added together, right? It's the sum of the squares, okay? So you take the sides, square each of them independently. You don't add them first, right? I square this one, and then I add it to the square of the other one. And then to solve for this, I just take the square root of the whole thing, right? Same idea here. Take the square root. I guess I can write it like this. Take the square root of each side. The square goes away on the left. We just get v naught equals, and when I plug my numbers in, I get 26.84 meters per second. And that's the magnitude of the velocity. That's not the velocity. Remember, velocity is both a angle and a direction. So how do we do the angle? All right. So we got this. We got this magnitude for the velocity. To get the angle, we're going to do, there's SOHCAHTOA, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Now, we could use any of them because we've now gotten the hypotenuse, but let's say you wanted to figure out the angle before you got the hypotenuse, you would use the toe apart. Tan is opposite over adjacent. So what that means is I consider the angle I'm interested in. This is the angle I'm interested in. And I'm writing it with a little arrow to remind us this is up from the horizon, right? You kind of swing it up that way from the horizon. So that's tangent. That's tangent of the angle is equal to the opposite over the adjacent. In this case, the opposite angle, the opposite side from that angle, opposite of the angle is V0y divided by the adjacent one, V0x. And to do this, there's a button on your calculator that says tan to the minus 1. It looks just like this. This is called tan inverse. And what it's going to do is it's basically going to cancel this tan the same way that taking a square root cancels a square, if that makes sense. So we're going to do tan inverse of our V0 y over V0 x. And that's going to give us our angle here. If you get an answer of 1.1, this is in radians, right? If you think about this, if I have a triangle that has one side that's 2 times as tall as the other side, it'll look something like this. And this is clearly not a 1 degree angle. Remember, 90 degrees would be to here. So that's not 1 degree and then this being 89. It'll look something close to this. So clearly 1.1, if you get that, that's in radians. And remember, there are 2 pi radians in 360 degrees is one way to do the conversion. Or you can just change your calculator to show degrees. And I think you get like 69.9 degrees, 70 degrees, something like that. So that is how I would approach this problem, and I went very slowly, but remember, literally all we did was this equation twice. This top equation, we did it twice once we got the time. And that was all. There wasn't any of this cut it in half stuff, That is useful because what we didn't solve for is we didn't solve for the height, right? We didn't solve for the maximum height of the throw, which is what part of the problem was originally, but I cut that part out. So I'm not expecting you guys to do this, but the problem was there was a lot of people who it looked like everyone just memorized the way that he solved it in the video. And that can be problematic because a lot of people didn't understand what happened. So if we look at this, you'll find we actually end up with the exact same answer. They're both completely perfectly valid ways of approaching it. What he did is he broke it into 2 separate pieces. He took the part of the problem where the ball is going up until it reaches its apex, and then the part of the problem where the ball is coming down from the apex until it gets to the ground. Okay, don't worry about the fact that they don't look the same. I'm just bad at drawing. Maybe I can do this. Take this, and then can I copy it? Make a paste, and then rotate it? Yeah. There we go. All right, now it's perfect and beautiful. So you take these 2 halves of the problem, and if we consider this, right, this is this is going to be at half of the total displacement in the x direction, right? This is going to go half the total displacement in the x direction, and then the last half of the problem, the last half of the throw is going to go the other half of the x displacement. The height, right, is going to be this change in y, with the final y being the height, and then the initial y being the height on the second half. There's an initial velocity in both the x and the y in the first half, which we know because that's what we're solving for. But the final velocity in the y up here is 0 because it's at the apex. And then the initial velocity in the y on the second half is 0 because it's at the apex. And then the final velocity down here, like I said, it'll actually end up being the opposite. It'll be the negative in the y direction. But It's not really important. We don't need it. So basically what was done here is, and what he did was he solved for one of these pieces to get the height, and then he used the height to get the initial velocity in the y direction. So if we look at it this way, and we kind of think about things, I just wanted to show where he got that equation that everyone was quoting from, because I was a bit concerned about just people throwing that equation out there with no lead up, no build up, and no indication of how they got there. When we give you equations, you need to use those equations, and there's a reason for it. That thing that he gave, which was, what did it look like? It was it V equals V0 plus AT or something like that? First of all, there's actually a bit of an issue here, but we need to be very careful about just throwing these out, because this is only valid for this problem, and I'll show you where we get there. So if you look at the second half, right? So we're going to consider the second half, and we can do SY equals V0YT plus 1/2 AYT squared. And if we're looking at the second half, SY is going to be negative height, right? Because it's going to go final, which is 0, minus initial, which is the height, right? So it's 0 minus height. I can drop the 0. It's just height, okay? Then we've got V naught y, and we said it's at the apex in the second half. At the initial on the second half is at the apex, so that's why that goes to 0 times time. Obviously, that's going to be 0. Plus 1/2, and we've got gravity again, negative 9.8, times the time, which he had solved for the same way. That goes in here. It's going to be 5.1. Actually, I'm sorry. That's the other thing. Since we're only dealing with half of the throw, it's going to be half of the time, which is going to be 5.1 over 2 squared. Make sure you put the over 2 inside, otherwise it's going to be wrong. So here, he solves for that, and he gets the height. I believe the height is 31.86 meters. So height, I can also just call that, SY for the half of the problem, right? Either half, that's going to be the SY. You'll either get negative 31.86 or positive 31.86, depending on which half you're doing. So, okay, so once he got the height, he then went back into the first half and used that to say V squared equals V naught squared plus 2AS. And if we look at the first half, right? First half, the final velocity in the first half, up here, it's at the apex. So this final velocity is 0, because that's the apex. Okay? And again, we're doing y. These are all just for y. The V naught is what we're solving for. Acceleration is 9.8. S is now going to go in here. And what you'll find is you get, basically, you get to solve for V naught y. And you get the same answer. But here's the thing. A lot of people skipped this step of how they got here. And what they did is they if we don't plug in the numbers and we look at this and we plug in this SY up here into here, what do we get? Well, we get VY squared equals V, I'm going to drop the y's because we're only dealing with y here. We get V squared equals V naught squared plus 2A times V0t, well, the V0t was 0, right? So we'll drop that. 1/2 AT squared. See what's happening? These 2's cancel. A times A times t squared. That's going to be V0 squared plus A squared t squared. Now, be careful, if I take the square root of both sides, I don't get V equals V naught plus AT. That's not correct because of this addition, right? I can't just cancel things like that when we have this addition. So the only reason it worked for this problem is because for the first half of it, V is 0. And when that's the case, when I have 0 equals V naught squared, let me pause this. Sorry about that. It's a couple hours later now, so if I lost my train of thought, I apologize. But basically, I was just saying this does not directly correlate to the equation he was showing unless one of these velocities, either initial or final, are 0. So we have to be careful about actually using that equation in these sorts of situations. Now, the way that it was set up, it was perfectly valid. It worked very well. But I still think that that first way of doing it makes a lot more sense for the question we were given. And then for solving the height, you could use that half. One of the things I saw a lot of people doing that I just want to address really quick is we can't be mixing our parts of the we can't be mixing our components. So I saw a lot of people who they clearly remembered that they were supposed to use v squared equals v naught squared plus 2as, and they were like throwing in the velocity that they got for x. So they solved for the velocity of x using the time and this, they solved for the velocity of x. And then they plugged that in, and then they said, oh, acceleration is 9.8 meters per second. And now what we've done is we've taken a y piece, we've taken an x piece, and we've combined them. You can't do that. It doesn't make sense. Acceleration in the y direction does not imply anything in the x direction, because remember, if there's no acceleration in the x direction, then v0 and v have to be the same, which would make sense, because we plug a 0 in here, and now v squared equals v naught squared, aka v equals v naught, which is the definition of no acceleration. So that was something I saw a lot. Yeah, just generally, I just wanted to kind of make this a video because I don't have time on this Wednesday to do this because we got to do circular motion. But I really thought that this was an important thing that I wanted to show everyone in a lot of detail. If you have watched all the way to the end, thank you, I guess. But hopefully you can use this to study. And if you didn't watch all the way to the end, you are not hearing my voice. So we're good to go. But yeah, good luck, guys.